All right, hello everybody, and welcome to the workshop on the Outer Planets Unified Searching for Planetary Mission Data via the API, given at the OpenPlanetary Virtual Conference on June 23rd, 2020. My name is Robert French, and I work at the SETI Institute in Mountain View, California. I've also been talking a lot already today, so forgive my voice. In addition to doing research on the rings and moons of Saturn, Uranus, and Neptune, I'm a co-I of the PDS Ring Moon Systems node and the lead developer of OPUS. As a reminder, this session is being recorded. Questions and comments are welcome at any time. To ask me a question, simply unmute yourself and interrupt me. Please keep yourself muted otherwise. All right, so OPUS, which hopefully you are already familiar with because you have either used it yourself or have watched the previous talk on it, has a public API which allows anyone who wants to access the data that is stored for searching inside of OPUS. This API is what's called RESTful. This means it is stateless and idempotent. So stateless means that there is no state that is stored on the server. Whenever you do something, you always get fresh information. You cannot do things like add things to a cart. You cannot change information on the server. Idempotent means that if you make the same query twice, you will always get the same answer. Now, that's not true if we change the database, of course. That doesn't happen very often. But if you call twice in a row, you will always get the same data. The API is accessed through the HTTP GET method only, not through POST or PUT or anything else. It uses URLs that are escaped using RFC 3986, the percent encoding, which I'm sure everyone is familiar with. It's all the little percent signs that you see in URLs all the time. But you can substitute a plus sign for a space, which makes the URLs a lot more readable. The endpoint of the API is the main OPUS site /opus/API, and we'll talk about all the things you can put after that in a minute. The arguments after this API name at the end start with a question mark, and then they're separated by ampersands. So you may have an API endpoint, and then a question mark, and then a series of key value pairs separated by ampersands. Depending on the particular API call, we support multiple return formats: JSON, CSV, HTML, or ZIP. And the normal OPUS URLs have the same format as the API calls. And this is actually very important because you can create a search in OPUS and then go look at the URL in the main OPUS UI, see what the fields are and see how they were used, and then copy that into your own API program for modification. There's full documentation available in OPUS, and let me show you where that is. So if you go to the Help menu and go to API Guide, there is a complete guide, both exhaustive and exhausting, detailing every single thing that we're going to be talking about today and a bunch more. You can either look at it in a new browser tab or you can download it as a PDF file. All right, so fields in OPUS are the things that you search on or the things that you return data about, and they're referenced by a thing called a field ID. Examples of field IDs at the bottom are things like planet, observation type, greater pixel size, OCC receiver host, which is occultation receiver host. Ones that correspond to a particular mission or instrument tend to have that mission or instrument as a prefix and be capitalized, just so that they're easier to read. The range fields, depending on the context, might have a 1 or a 2, and we're going to talk exhaustively about that in a few minutes. But the string and multiple choice fields never have a 1 or 2 at the end. So the first thing that you might care about is how do you know what fields are available? And for that, we have an API call. So there's a fields API that returns either a JSON or a CSV, your choice. And that gives you a list of all of the fields that are available in OPUS. So we're going to do a lot of this as actual demos. So I am going to do OPUS API fields.json. And one reason I'm demonstrating this in Firefox and not in Chrome is that Firefox has a really cool way of displaying JSON return data, which is it either parses it out for you and shows it to you as a nice tree, which you can then expand each individual field of, or you can look at the raw data and you can pretty print it. And I think that's much nicer than looking at it. This is what Chrome would show you if you looked at it, which is not nearly, oops, I have a lot of data here. It takes a minute. There we go. So if I don't pretty print it, it looks like this. It's a lot harder for us to read during this talk. So here is the JSON return from fields, and you can see For each one of these field IDs, like planet or target class or whatever, there is a series of information. There's what its label is, its qualified label, what units it has, what its default units are, what category it is on the main Opus search page, and this just gives you a list of what is available in terms of fields. But one thing that you will notice is that if you look at the list, there is a separate field for every single body that we have surface geometry for. That is a lot of fields. Notice all the Enceladus fields, and then all the Hydra fields, and then all the Kerberos fields. And you may not, as a human, want to see all of those, because for each body, there's exactly the same set of fields. It's basically a template. Okay? Now, if you're writing a programmatic interface, you probably care about all of these. If you're a human, you probably don't. So we have an extra option here called collapse. If you say collapse equals 1, what it does is it takes all those surface geometry fields and it replaces the target body with just the name target, and it only gives you one copy of them. Okay, so this makes it a lot easier for you as a human to read. Notice there are many fewer returns in the fields return at this point. Now, the other thing that you can do is we're going to get rid of this one, you can ask for information about one particular field. So I can say, instead of fields.json, I could say fields, and let's say I care about planet. And now I can get the information just about the particular planet field. Okay, so this is basically cut and pasted directly out of the API guide. It gives you information on what each one of those return things means. I won't go over it into detail right here. I'm just trying to give you an overview during this discussion. All right, so now that you know what the field IDs are, you can use them to search. There are fundamentally 3 different types of fields that we have in Opus. There are multiple choice fields. Those are the ones that are in the UI, have checkboxes next to them. There's string fields, which we didn't get a chance to demo in the last talk, but are ones where you can just type in a string. And the third one is range fields, where you can search on a range that has a minimum and a maximum. So for multiple choice fields, you can search just by having the field ID and then having a comma-separated list of values that you would like to be in your search results. So this might be Jupiter, comma Saturn, comma Pluto. For string fields, you can have a field ID and then just the value you want to search on. And again, remember this has to be percent encoded if it has any special characters in it. Now, string fields have an optional thing that we didn't unfortunately get a chance to talk about before, which is just like range fields have a query type of any, all, or only that specify how the search is going to be done. String fields also have that kind of query type, but they're different names. And let me actually just show that to you real briefly here so it makes sense, which is that if I search, I'm going to start over. Let's say that I search on a string like volume ID. If I were to type COISS, there are different things that could mean. It could mean I wanted to search on a field that contained it anywhere, that started with it, ended with it, matched it exactly, excluded it, or maybe this was even a regular expression. So this little drop-down over here allows you to choose which one of those particular types of match you're doing. These are exactly the same things that you can put in the API so that you can, so that you can say, I would like to have this value to search on, but I would like to do it using contains, or begins, or ends, matches, excludes, or regular expression. If you don't specify it, the underlined version here, which is contains, is the default. Now, range fields are slightly different because you have to specify both a minimum and a maximum for the same field. And in that case, what we do is we put 1 or 2 suffixes on the main field name. 1 means minimum, 2 means maximum. Once again, there is a query type you can specify, which is one of any, all, or only. And here you can also specify a unit, where you say unit dash and the field, and specify the unit name. And we'll give examples of all this in a minute. Don't worry if this isn't making sense yet. Okay, so the last thing you can do, we talked earlier about the fact that you can have multiple copies of the same search field, and it orders them together. So to do that here, there's an optional suffix that you can put on a field name, which is a number. You can say underscore and then some number. It doesn't really matter what the number is, as long as it's positive and not 0. you could have multiple copies then of a field. You could have _5, you could __ 10, and each one of those is counted as a separate search term, and they're ORed together. If you're going to specify the query types or the units for one of those fields, the _in value needs to agree with the _in that you specified for the particular field. So they go together as a grouping. So here's an example. Let's say that I wanted to search on either a volume ID of COISS _2001 or a volume ID that contains VIMs somewhere in the name. So I could do _1 on the first volume ID and say that the query type of volume ID _1 is matches, which means that this has to match exactly. Then I could have a second search, which is volume ID _2 for VIMs, and say that the query type for that is contains, which means that VIMs must appear somewhere in the search in the result string, but doesn't have to be the only thing that's in that string. Okay, so here's a long example. So earlier, we were doing a search on Saturn's Great White Spot. Here is the actual search that we ended up doing as it was encoded in the OPUS URL. So one of the things that we did, if you remember, is we made sure that the maximum number of missing lines in the image was 0. So that's COISS missing lines 2, which is the maximum field, is 0. We made sure the observation type was image. The finest resolution for the surface geometry of Saturn went from 100 minimum to 300 maximum. It had INI, which is the default, and it had units of kilometers per pixel, which is also the default. I've italicized these here to indicate that if you didn't include them in your search string, nothing would change. Then we had surface geometry on Saturn for the longitude, so minimum longitude of 230, maximum of 10, and again, INI and degrees. Then we had the latitude from 40 to 55. We had the time, went from December of 2010 to December of 2011. And we had the wavelength. And here's where it gets interesting because we did some funny things with the wavelength. So our first wavelength query was from 647 to infinity microns. Sorry, from 0.647 to infinity microns, but I've chosen here to represent that as nanometers. So that's 647 nanometers. So I specify only the one version, which is the minimum, and I specify 647 with a unit of nanometers. I had to override that default unit. We also wanted the only style of range matching, so I had to put a Q type in here, which is the Q type of only. Notice they all have the same underscore numbers. It doesn't really matter what the number is, again, as long as they match. Now our second wavelength query was specifying the maximum so that we could have all the blue images. So here's 492 nanometers as our maximum, and again we had an only query type. All right, I would like to pause just for a second and see if anyone has any questions because we're going to run with this type of search for the rest of the talk. All right, so hearing none, we can actually do some real API calls now. So the first thing that you want to do is to be able to get generic information about your set of results. So, for example, you may want to know how many results there were. We have a basic API for that called result count.json, which I have is meta API meta result count.json, and it simply returns the number of results. And you may recognize this number. It's the number that when you run Opus from scratch, it is the number of results that you get when you haven't specified any search criteria yet. Okay, now I can also do that returning a CSV value. I'm going to open that in my browser as a text file and say there's the CSV. Okay, so if you find it easier to parse CSV for some reason, you're welcome to get it back as a CSV file instead. Let me see, where is I here? Okay, you can also specify constraints. So for example, I could say that I would like to look at only ones of Jupiter and Earth. So here I specify constraints for the planet. And notice that my result count is now smaller than it was before. Maybe I only want to do it for a range. So here's something with the observation duration. Okay, result count, observation duration minimum is 10, no maximum. So anything that is 10 or greater in observation duration, there's the result count for that. Okay, and again, you can continue on with more and more complex search queries like we already talked about. Just to give one slightly, interesting one like we just talked about, here's the one with the strings. So here's, it must match COISS 2001, or it must match COISS 2002. Okay, there's 7,000 of those. If we want to do the exact one that we did earlier, we can say maybe we want the second one to be VIMs, and we want it to only contain VIMs. This one has to think about for a minute. And there we go, 743,000 results in that result set. All right, so the next thing that we can do is we can ask for the possible values for multiple choice fields. So this is not only a list of the possible choices, but it also includes those green numbers that we talked about, saying how many search results there are for each one of those fields. So again, this is meta/mults is the particular API endpoint that we're going to do, and you must specify the name of the particular field that you care about. So let's say that we only want the mults for planet when there's no specific search constraints being imposed. So here it is returned the list, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and other. And these are the same numbers that you would see in the OPUS UI if you looked at these fields right here. Okay, again, I could constrain whatever the search is. So for example, I could do a fancy search that involves wavelengths, like we talked about earlier. It's only looking at images, only looking at wavelengths that are in a particular range, using the only range type and all specified in microns. And oops, and I actually hit a key at the end. And there are the results for that particular search. Finally, you could do one for target, and there are a lot of targets, and I will just show you that. So here are all of the different targets. Finally, the one other type of metadata that you can get back is the endpoints for numeric fields. So if you remember from inside of OPUS, if I search for something like, let's say, ring radius, I get a range of values here that are sort of like these green numbers here, but this is the minimum and maximum of all observations that match the current search constraints. So I can do that with this by saying, again, I have to specify a particular field that I care about. So let's say I care about observation duration of all observations in OPUS, and it returns, here let me look at it in raw, a minimum of 0, a maximum of 260,000. They're nulls, which means these are observations that don't have durations. There are 142 of those, and the units are in seconds. Okay. Currently, there is no way to, and so there is a way to override the units for this by specifying a question mark unit dash observation duration. All those details are in the API guide. All right, so moving along, the next thing that we can do is we can talk about how to actually get the metadata for particular observations. And this is probably the most confusing part of the entire talk. And if this is the only thing that you get out of the talk, it was worth your time to listen to it. So as we talked about earlier, there is a field ID. And for searching, let me just page back here so you can remember. For searching, if you have a multiple choice field or a string field, you just give the field ID and the value and you're done. If it's a range field, for searching, you always search on a minimum and a maximum. They're optional, but you have the ability to search on both. And for those, you put a 1 or a 2 at the end of the field. So for the purposes of searching, and I'm going to keep repeating this, a 1 and a 2 means you're searching on the minimum value and you're searching on the maximum value. When you are returning data, the 1 or the 2 means the minimum value stored in the database for one observation, or the maximum value stored in the database for one observation, in the case where you actually have the minimum maximum available to you. If you do not have minimum maximum both available to you, and this is going to be a typo here in a second. So for example, observation duration. only has one number in the database. There's no such thing as a range of observation durations for one observation. So you search on it using the 1 and 2, but you only retrieve it by using the root ID. Okay, there's no 1 or 2 because there's only one value that you can retrieve. Now, this is a copy-paste error, and I apologize. I will fix this before sending it out. If we picked a 2-value range field, so let's say we took ring geometry radius, for example, and just pretend this does not say observation duration, pretend this says ring geometry radius. Again, to search on it, you would specify 1 and 2 for the min and max, but to retrieve it, you would also specify the 1 for the minimum value and the 2 for the maximum value. Okay, so very important, you cannot use 1 and 2s to retrieve if the database doesn't have actual minimum and maximum values stored in it. And if it does have them stored in it, you must specify the 1 and the 2. You may ask, how do you know which type of field it is? And the answer is, when you go and you retrieve the list of fields, you will either get back, oops, let me just do it this way. So for example, for observation duration, there is a single observation duration that got returned. Okay, but for wavelength, for example, there are 2 wavelengths that got returned. That tells you that in the database there are 2 fields and that you need to use the 1s and 2s when retrieving the metadata. I know it's a little subtle, but it's not bad once you get used to it. So, if we want to retrieve the search results for a particular search, we want to specify a couple of things. One of them is we want to specify the order of the results returned, so that's the sort order. We want to specify which particular fields we care about. And because there may be a lot of observations that we're returning, we want to specify a window into those observations so that we don't have to get all 1.5 million back simultaneously. So to do that, we can specify a starting observation, and we can specify a limit on the number of observations returned at once. Okay, so the order is the sort order that we specify, and again, you can specify multiple fields, so it can search first on filter, and then on wavelength, and then on time. If you put a minus sign in front of one of the fields, then it sorts in descending order rather than ascending order. Ascending order is the default. If you don't specify any columns, it will return the default set of columns, and if you don't specify a sort order, it will do the default sort order. If you don't specify starting observation, it'll start at the beginning, and if you don't specify limit, it always returns 100. So, let me give you just one example here. So here, we're going to return the data in JSON format for observations having to do with Earth. If you remember earlier, there were only 10 of these. We care about the OPUS ID and the starting observation time, and we only want to get 2 of them back. So here we go. I'm going to look at this in raw data format and show you what we get back. So we always get back a copy of what we asked for. So we asked for the starting observation 1, it tells us there's 1. A limit of 2, it tells us 2. The count tells us how many it actually returned, because it's possible we asked for 1,000 and there were only 50 available, in which case it's going to tell us there were 50 that were actually returned. The available tells us how many there are total in the entire result set with this particular search. So there are 10 observations of planet Earth in the entire database, so there are 10 available. This means you do not have to do a separate result count call in order to figure out how many there are, because every time you ask for data, it just tells you. So this tells you if you've reached the end, if you want to window your way through the data returns. It also tells you what order you asked for. If you didn't ask for an order, this is the default order, starting time followed by OPUS ID. Here are the labels of the fields that you asked for. Columns is for backwards compatibility. You won't find it in the API guide. And then page is the actual page, what I'm calling a window of data that you asked for in the same order. So here's the OPUS ID for the first one. Here's the starting time for the first one, OPUS ID for the second one, and starting time for the second one. If you want to do something like specify a different sort order, if I can type properly, I could do, reverse it by time and start with observation 3 in the reversed order, and there we go. All right, so we can then go on and talk about getting metadata for one OPUS ID. So instead of specifying a search, you can specify a particular OPUS ID. So let's say, and for historic reasons, this is called metadata version 2 because the original metadata didn't work very well, but we wanted to keep it for backwards compatibility for a while. So this one is now called version 2. So you can specify an OPUS ID, you can specify a list of columns like we already talked about, or you can specify a list of categories. Now the categories are the things that you see on the main OPUS page on the left. So like PDS constraints is a category. So you don't have to list every individual field one at a time because you can specify categories. Also in this case, if you don't specify anything, you will get all of the metadata back. Okay, so you don't have to go and list every single possible field or every single possible category if you want all of the data. So before we do the categories, you may ask, where do you get a list of the categories? And conveniently, there is an API for that. So I can go and ask for the categories, for example, for a particular search. So here's the categories for instrument UViz. This will take a moment, and here we go. So it gives us a short name, which is basically our internal database table, but you can still use it. So like OBS General, OBS PDS. Sure, at least, no problem. And it has the pretty name, which you could specify as well. So if I wanted to go and get the values for, let's say, this particular OPUS ID, and this is going to return everything, there is all of the metadata we have available for this particular observation. This is the same stuff that you would see on the Detail tab. But let's say we only care about the details for some of the things, and not all of them. We can then specify, for example, that we want just the wavelength and just the image constraints. Notice I've mixed and matched here, whether I use the short name or the pretty name, it doesn't matter. And here we go, same thing. I'm now getting the image constraints and I'm getting the wavelength constraints back. Okay, any questions about that so far? I know going through an API call by call is kind of boring, so thank you for sticking with us. All right, the next thing that we can do is we can retrieve the actual PDS files that are associated with particular observations. So these are the ones that you would actually download from the PDS server in order to get the actual products. So you do the same search, same sort, same starting and limit, but now you specify a series of product types. And if you remember back in OPUS, we talked about for a particular observation, there are these particular product types here. These are the product types that we're talking about specifying in the API. Again, if you don't specify any product types, you will get all of the products, but you can also limit it. In addition to getting the files for a particular search result, you can get the files for one particular OPUS ID, and again, you can limit it by product type. So, where do the product types come from? Well, once again, there is an API for that, just like there was for categories. And I can say the product types, let's say for Cassini RSS, the radio science system. So here are all of the download types that are relevant for this particular search. So these are, Cassini RSS was only used for occultations. So here are 1 kilometer profiles, 10 kilometer profiles, diffraction limited profiles, calibration parameters, and the geometry parameters. So those are the 5 types of product types that I could download for Cassini RSS. So if I wanted to get a list of the files for all of the RSS observations, I'm going to show it to you in raw data here, pretty printed. Okay, so in the data section, it's going to tell me for any one OPUS ID, here's the particular product type, and here are the files that are associated with it. So there's always a table file and a label file. So there's the 1 kilometer, there's the 10 kilometer, diffraction limited. There's our 5 types of files for the first OPUS ID. For the second OPUS ID, here's the 5 files. For the third OPUS ID, there's the 5 files. Okay, so you can see from this, you could create your own list of things that you would then be able to wget or curl or use your Python interface or whatever, and you could fetch these individual files from the PDS server. This is the actual URL that you would use to retrieve them. But let's say that we didn't care about all these different types of products, and we only wanted the 10-kilometer occultations, and we only wanted the first 2 of them. Okay, so now we can put our types limiter on it, and we can put our limit, and now we will get just the 10-kilometer one for the 2 OPUS IDs. Okay, now since there are fewer results here, I can show you something else, which is the versions. We have the data section always gives you the current version. For some of our products, we have multiple versions that have been changed over time. As an archive, we always keep the old versions of the products around. So in the versions, you would then have a list of different versions that are available, and you would be able to get the files for each one of those versions individually. So, for example, New Horizons has multiple versions. So if we look at not the data, but at the version section, there is version 1, and here are the files associated with version 1, version 2, version 3, and then the current version. Okay. Normally you only want the current version, but you never know, you might want the old one for some reason. Now, so here is for this one particular OPUS ID, here are all the files, version 1, 2, 3, current. Now here's the next OPUS ID for all the versions, 1, 2, 3, current. So lots of information available for you to download from. Finally, you can get the files from a single OPUS ID. So here it is, for example, for this one Galileo observation. And exact same thing, except that instead of doing a search, we just specified the one observation that you cared about. All right, so we can do exactly the same thing for images. Images are those preview images of various sizes that we've been talking about all afternoon. There are 4 sizes of images. There's thumbnails, smalls, mediums, and fulls. Generally speaking, but not guaranteed, thumbnails are 100 by 100, small are 256 by 256, medium are 512 by 512, and full are 1024 by 1024. Most of the time, not always. Okay. Once again, you can get images back from an entire search. You can ask for just one size from an entire search, or you can ask for one OPUS ID of one size. This is a very convenient way to download those preview images if that's the main thing you want. If you want to load them into Photoshop or something, it's those preview images that you probably want to play with. Let me give you an example here. For example, here are all of the images from Galileo's SSI. Notice that it automatically gave me a limit of 100. It returned 100, but there are actually 3,846 of them available. So if I wanted all 3,846 of them, I could either go back here and put at ampersand limit equals 3846, or I could make multiple calls to the Images API with a different starting observation each time. So we get a little different information with the images than we do with the files. So for each one of these entries, let me go again, it's easier to look at here, we get the OPUS ID, and then we get the information about thumbnails, small, medium, and full. And for each one of those, we get the URL of the actual image, we get the alternate text, which is just the basic file name at this point, and then we get the number of bytes in the JPEG file and the width and height in pixels. So notice, for example, this one is not 256 by 256 for the small, it's 114 by 200. So they're not always a constant size. The medium is 191 by 334 in this particular case. Okay, but this gives you information about the images that you do not get just by calling through the files. The Files API gives you the list of images because they are actually download products, but it does not give you the details about the images themselves, like pixel size or the size of the file. Okay, so you could also download this, for example, as a CSV file. So let's do exactly the same thing, except do images.csv. We'll open as a text file, and here you see we have a header in our CSV file, and then there's a comma-separated list of URLs, one per OPUS ID. So maybe that's easier for you to use. You can also specify a particular size. So I only want the small images. And now when it returns, you don't get all of the different sizes, you only get the information for the small for each OPUS ID. Again, you can do that in CSV. You can also get that in HTML, which is kind of cool, because that lets you actually look at the images directly. if you look at the source for what it returned, it basically is returning just a list. And so if you have whatever code that you want to incorporate these preview images in your own code, you could simply substitute this HTML inside of a div or something like that, and then apply appropriate CSS formatting, and you would end up with a nice set of preview images. Okay, finally, you can do exactly the same thing, but for individual Opus IDs. Okay, same thing as doing the search, except you're specifying just one ID. There are a few products that we have that we do not yet have preview images for. That currently is occultations. So if we ask for the images for occultations, for example from Cassini RSS, you simply get a list of the Opus IDs, and then there is no information in them about the images, showing that there are no images that are available. Finally, we have one remaining API call, and that is for downloading products. Now, obviously, you could take what we already gave you, you could use those URLs, and you could retrieve the files one at a time. And that's actually probably what you want to do if you want to do retrieval of a lot of different products of a lot of different files. We do not supply you with the basic cart concept that you get through the UI. As I said, the API is stateless. It does not remember what you've asked for or what you've saved, so there is no cart concept. So all we do here is we let you download products for one Opus ID at a time. You can't do it for a search, you can't do it for a cart, just one Opus ID. And you can only download it in zip format. If you remember back in the main Opus interface, there were two different types of downloads you could do. You could do a data archive, which includes everything, and you could do a URL archive, which only includes the list of URLs and the manifest file. And we, again, allow both of those through the API by this optional parameter at the end. Okay. Once again, I have a typo here. There are no same search fields here, but there are product types. Okay, so you can specify which product types you want, and it returns a zip file containing just those products for the given Opus ID. If you don't specify types, it returns everything. So earlier, we did not get a chance to look at the details of one of these, but let me just do that now. And here is the zip file for one Cassini ISS observation. And I am going to open it. Let's see, I'm going to open it as in Windows Explorer, and then I'm going to change my screen sharing so that you can see what I just opened here. All right, so here is the list of files that is in the zip file that I just downloaded. You can see that there are the individual image files for that one Opus ID. There are the preview images, the full, medium, small, and thumbnail. These particular JPEGs are extra preview images that were supplied by the Cassini team. There is the manifest file and a URLs file, and then there are the inventory and summary files, which give you all of the ring geometry and all of the surface geometry for all the bodies in this particular volume, the entire volume, not just for this one observation. So with that, we are done. And let me pop back to here. And I will say thank you to everybody. As always, we love feedback. We love comments. We don't hear from our users nearly enough. And I will stop at this point for any questions.
Hi, this is Julia.
Hi.
Hi. Just to say, I'm totally new to all this concept of the two workshops you just did. So I was just wondering why I would do a search through the API. So what you just went through, rather than using the first thing we saw in the first workshop.
Sure, it's a great question. I think that 99% of our users would use the web interface. Let's just start with that. I mean, yes. It's user friendly. It lets you browse. It lets you download. It's what we put a lot of work into to make it usable not only for scientists but also hopefully for members of the general public to find pretty images and to download things that they find interesting. It's one of the reasons that we let you download those JPEG previews, because that's of more interest to the general public than the actual raw data would be.
Mm-hmm.
The API is useful to a fairly small set of researchers who want to use software that they've written to
Mm.
go and query information. So perhaps there's a researcher who is trying to explore particular parts of Saturn or particular sections of the ring, and they would like to explore them chunk by chunk. So maybe there are 400,000 images of Saturn's rings, but they don't want to download them all and look at them one
Mm.
at a time. They would like to say, well, let me try the first 100 and then see what's in there, and then try the second 100 and see what's in there. In the web interface, that's actually really hard to do, right? You have to add them to your cart chunk by chunk, download them one at a time. It's a real pain. But if you write a
Mm-hmm.
piece of software to do it, it's really easy to do.
Makes sense
Right,
now.
right.
Mm-hmm.
And also there are different types of searching that people might want to do that you can't do during the web interface. So, we limit the kinds of comparisons you can do. So, for example, you can really only do searching on one body at a time. So latitude and longitude on Enceladus, and then you're stuck with Enceladus. If you want to look on some other body, you have to get rid of Enceladus. The API
Mm.
actually does not have that restriction. So you could search on parts of Enceladus at the same time you're searching on parts of Callisto, at the same time you're searching on parts of Saturn. So the API in some ways is actually more flexible than what we've had to limit the web interface to, so that the web interface was more usable.
Mm-hmm. Thank you.
Mhm. All right, I will go ahead and stop the recording.